you know that there is something in physics called the principle of parity. This is that particles can appear out of nothingness as long as they appear in pairs, such that after a certain period of time, the two pairs and not the two portion, the members of the pair encounter and annihilate each other. And when this happens, physicists say parity is conserved. Now, it's known in quantum physics that there is a phenomenon called vacuum fluctuation. Vacuum fluctuation is a situation where in absolutely empty space, suddenly out of the quantum subspace, particles jump into existence. They follow trajectories, they encounter each other, they annihilate each other, parity is conserved, and so it's okay. It's okay. Well, so then you talk to these quantum physicists and you say, well, how large can one of these vacuum fluctuations be? And they say, well, most of they last milliseconds, nanoseconds. You say, well, is there a theoretical upper limit on the size of a vacuum fluctuation dictated by theory? And they say, no. It's simply that the longer the fluctuation lasts, the rarer it is. So in other words, the longer a fluctuation lasts, the less likely you are to encounter one. Well, then you say, well, is it possible that this entire universe is such a vacuum fluctuation? You say, well, yes, but that would be very rare to have such a long one. You say, well, hell, you only need one. Calculating the probability of a unicate event is a fool's game. I mean, it's either 100% sure or 0 sure. So here is a model, and I took this from the Swedish physicist Hans Alfvén, who hasn't gotten enough credit, but who's really a very interesting thinker. Imagine that the universe is this kind of vacuum fluctuation, a 17 billion year long vacuum fluctuation. Well, what it means then is that at the Big Bang, not one universe was born, but two. And they sailed off into superspaces and have no connectivity with each other, or they have Bell non-local connectivity or something. But anyway, they are distinctly separate. But they are, unbeknown to each other, on a collision course with each other. Parity must be conserved eventually. And a model like this holds open the possibility of the instantaneous transformation of the entire cosmos, because the collision of these two universes would not occur in three-dimensional space. It would occur in a higher dimensional space. So this cosmological model holds out the possibility that all matter in the universe could be instantaneously canceled in this encounter with the antimatter twin that was born at the beginning of the cosmos. Okay, if you're still following, we're almost to pay dirt. Every particle known to physics possesses an antiparticle, which is locked into this parity-conserving thing I've laid out for you, with one exception, one astonishing and amazing exception. The photon has no antiparticle. There is no antiphoton. So this universe that is on a collision course with itself in hyperspace, at the moment of the conservation of parity, all matter vanishes. And what is left is a universe made entirely of light. And we have no model or I have no model for a universe made of light. There would be no gravity, because gravity is a property of matter. Such a universe could be modeled. And then the question is, well, then what would happen to forms? What would happen to your body, my body, this planet? The answer is no one can know. But it is very interesting that the esoteric traditions of nearly every religion talk about light a great deal, talk about ascent to the light, cultivation of the light, the after-death vehicle as a thing made of light. So I just put this out here because it occurred to me. My imagination, in an effort to make the assumptions of novelty theory congruent with the known laws of physics, I discovered, this sounds like wild hair stuff, but no violation of the known laws of physics is involved in this scenario. So perhaps what enlightenment is it happens to an entire universe when it drops its matter and antimatter out of its structure, and it becomes entirely made of light. That would certainly fulfill the novelty theory. Anyway, that's enough of that malarkey. Well, you see, the way the novelty theory is structured is you have this wave, and it is iterated on different scales. And iteration, if you have a given level, let's call it A, above A is a larger level that is A times 64. Below A is a smaller level that is 1/64th of A. And wherever you are in the hierarchy, this is true. Levels above, 64 times larger. Levels below, 64 times smaller. Well, modern astrophysics says they're arguing about it right now, but the universe is under 20 billion years old. Everybody agrees on that. And the question is it 9, 12, 13, 14? But it's under 20. The time wave has a cycle, the largest cycle I have found necessary, except for the prime number research, is a 72 billion year cycle. So let's call that the top cycle, the A level, a 72 billion year cycle, plenty of time for the universe to evolve to its present state. Below that level is a cycle 1/64th that size. What would that be? Roughly 1.2 billion years. At the initiation of that cycle, I don't know, some dramatic thing happens in biology. Below it is another cycle. If the B level is 1.2 billion years, then the next level is 1/64th of that. I think it's roughly 275 million years. Next cycle, divided by 64, whatever it is, 750,000 years. Next cycle, and you see where I'm going. Well, eventually you get to a cycle that's 4,306 years in duration. That is basically the cycle of late history. I mean, certainly there was history before 4,000 years, but the continuous march of global civilization over the last 4,000 years. Well, then the next cycle down is only 67 years long. And I mentioned it last night, from 1945 to 2012. Each cycle begins with a bang, literally. Below the 67-year cycle, there is a 384-day cycle. And that will run from late 2011, somewhere in November 2011, to the end of 2012. And I call that the year of the jackpot. It's a 13-month year, but the entire history of the universe will be reprised in that 384-day period.